We are in Rosen, Discrete Mathematics and its Applications, section 13.4 on recognizing languages. And here we discuss Kleini's theorem. In 1956, Kleini established connection between regular sets, which are defined by regular expressions, and sets recognized by a finite state automaton. Here's his theorem. He showed that a set is regular if and only if it can be recognized by a finite state automaton. That's Kleini's theorem. And there's a connection, as hinted at earlier, between regular grammars and regular sets. Remember, regular grammars are type 3 grammars from 13.1. And we say that a set is generated by a regular grammar if and only if it is a regular set, and then by theorem 1, i.e. recognized by an FSA. That'd be by theorem 1 above. Kleini's theorem. First we will tackle the proof, a portion of the proof of theorem 1. So we'll be assuming that a set is regular, and then we will show that it is recognized by an FSA. That is the only if portion of the theorem. And the way we do that is remembering that we have the basis steps for creating regular sets and the recursive steps for creating regular sets. We will show that in each case we can recognize the regular set by a finite state automaton, and in so doing prove that any regular set can be recognized by a finite state automaton. And the way we do this is we start step by step down this list, and we'll show that the empty set is recognized by a non-deterministic finite state automaton. But what is another name for the empty set from the earlier joke? It's nothing is recognized by a deterministic finite state automaton. That's the finite state automaton with no final states, and then that is an example of it right here. This is the finite state automaton that recognizes nothing, or said another way, doesn't recognize anything. All right, then we need a finite state automaton that recognizes the empty string, and that is the finite state automaton that is in a recognition state at the very beginning. And then a finite state automaton that recognizes a single symbol, has a start state, it is non-recognition, but has a next state upon input of that symbol that is a recognition state. And these take care of the basis steps of building up a regular set and building up a finite state automaton that recognizes it. The next one on our list was to create a machine that recognizes the concatenation of the language generated by the concatenation of two sets. And so we exhibit that here, where we have a machine that recognizes the set A and a machine that recognizes the set B. So this is a concatenation of A with B. And when we read a word from this concatenation set, it starts with a word from A, which works down the states, and then right before it gets to its final state, that last symbol will cause the machine to jump to the first state of the machine that recognizes elements of B. And then it will continue down its trail to get to final states for all elements of B. If A has the empty string as one of its elements, then SA will act as the first state for machine B. And then if Final states will be all the final states of B, so that if lambda is an element of the language of B, this will be a final state. And whatever the final states are, this is just an arbitrary machine, and it would have final states wherever language B required. SA becomes the start state for both machines, and it is final only if it's a final if and only if SA and SB are both final. But if SA and SB are not both final, if only SA is final, then we take its finality away, and it just acts as the first state for B. Okay. Now we will look at the union of two sets. And here we have machine A and machine B. And if we want to recognize the union of sets A and B, these two machines operate in parallel with a new starting state that acts as the original starting states for machine A and machine B. And then it will, whatever word comes in, it's going to work down both of these. If it's recognized by A, it'll get to the final state of A. If it's recognized by B, it'll get to a final state of B. And we'll recognize the union, therefore. So all the final states are the final states of machine A and machine B. And then the start state is final if either SA or SB is final. And then finally, we have the Kleene closure step. So remember, Kleene closure is just an arbitrary number of concatenations of set A. And we create a start state that is a recognition state because remember, lambda is always an element of a Kleene closure. And it replaces the start step of the original machine that just recognizes A. And then it goes down the list until it recognizes a word from A. And then if there's going to be another word from A concatenated to that, then the final state becomes a starting state and goes down and just continues around, and it will always recognize a word from A no matter which one it is. And that is how we can build up we can build up a finite state automaton for any regular expression.